Hi everyone, welcome back to Audio Develop. Welcome to episode 2 of our series. It's good that you're here. So today we're going to talk about the real-time audio callback and the foundation of audio programming. So in this episode we are going to write our first audio callback, the function that the operating system calls thousands of times per second and actually expects us to fill with audio data before the deadline. So by the end of this video, you will have a working sine wave generator running through PortAudio on macOS, Linux, or Windows. And you'll also have a timing measurement system that tells you exactly how much headroom you have in your callback and a clear understanding of the contract you enter when you write audio code. So why audio callback matters? When audio application on every platform runs through a callback, for example Spotify's playback engine or Logic Pro, or every phone call you have ever run through one, there's an audio engine that is running in that application. When the callback works, the user hears clean, uninterrupted audio. When the callback misses its deadline even once, the user normally hears a kind of a glitch or a pop or a crack, or we can call it a stutter. So in professional audio, a single dropout during a live performance or a recording session can actually ruin the entire tech and cannot be recreated. In a communication application, glitches destroy speech intelligibility and make the users switch to a competitor's app. What happens at the hardware level when your computer plays audio? Because once you understand this, everything about the audio callback will make sense. So your computer has a piece of hardware called a digital to analog converter, a DAC. So the DAC takes numbers and turns them into voltage. Those voltage changes drive your speakers or headphones, and the speaker cone moves. And that movement pushes air, and that air pressure wave reaches your ear. And that is when you're able to hear sound. So the DAC needs a continuous stream of numbers. It consumes them at a fixed rate, sometimes at 44,100 or at 48,000 numbers per second for each channel. So that rate is what we call the sample rate, and I had talked about the sample rate in the first video. So normally if the DAC runs out of numbers, it has nothing to convert. So the output normally goes silent, or it replaces the last buffer, or it outputs wherever garbage was left in the memory. So the user hears this as a dropout, or we can say it's actually a kind of a brief interruption that is immediately and definitely obvious in any audio content. The operating system manages the flow of numbers to the DAC, and it also maintains a buffer. So a buffer is a block of memory that actually sits between your application and the hardware. So the operating system periodically normally asks your application to fill that buffer with a new audio data. So these requests normally comes in form of a function call. That function call is the audio callback, and it runs on a dedicated thread. So that thread is what we call the audio thread. So this is the audio thread. So the audio thread is very, very, very special. On every operating system, the audio thread normally runs at an elevated scheduling priority. So on macOS and iOS, it actually runs at the highest priority below the kernel. On Windows, there's what we call the Wasapi exclusive mode, which uses the media class scheduler service to boost the audio thread to Pro Audio priority. On Android, there is the A audio and the OBO request scheduling. these are normally, it is actually the highest priority available in the Linux scheduler. So the reason for this elevated priority is that audio has a hard deadline. In your callback, if your callback does not return in time, the audio output normally breaks. There is no re-entry. There is no try again next frame. The moment is actually gone. So think of it like a conveyor belt in a factory, or in a processing plant. The belt moves at a constant speed. So your job is to place a finished product on the belt every time a slot passes your station. So if you miss a slot, it goes by empty. So you cannot stop the belt, you cannot slow it down, you cannot go back and fill a slot in case you missed it. All you can do is just be ready every single time. So normally the deadline is determined by two numbers. Number one, the sample rate. Number two, the buffer size. So at a sample rate of 48,000 hertz and a buffer size of 256 samples, the callback fires every 256 divided by 48,000 seconds, which is about 5.33 milliseconds. So that is your entire budget. Your callback must execute. So fill all 256 samples for every channel and return. So before those 5.33 milliseconds expire, if it takes 5.4 milliseconds, you miss the deadline. So there's one dropout. At a buffer size of, for example, 128 samples at 48,000, the deadline drops to 2.667 milliseconds. So at 64 samples, it is 1.33 milliseconds. So professional audio interfaces on macOS routinely operate at 64 or even 32 samples. So the smaller the buffer size, the lower the latency. But also the tighter the deadline and the less room you have for anything unexpected. We are going to do our first callback, the sine wave generator with PortAudio. So we are going to write our very first audio callback. The goal is specific: generate a 440 hertz sine wave, the standard, and not above the middle C, and play it through the default audio output device. So we are using PortAudio because it gives us a single API that works on macOS via callaudio. I am on macOS. On Linux via ALSA or Jack. You remember I talked about these. And Windows via Wasapi or Direct Sound. So these will actually let the user focus on the callback itself without getting tangled in a platform-specific setup that we will, cover in detail in later chapters. We need to write a function that the audio system calls repeatedly. And each time it is called, we need to fill a buffer with the next chunk of a sine wave. So the sine wave generator concept, we need to write a function that the audio system actually calls repeatedly, and each time it is called, we need to fill a buffer with the next chunk of sine wave. So the naive approach will be to compute, the STD sine 2 times pi times 440, times t for each sample, where t increments by half a sample rate. So each sample, so that works mathematically, but has a problem. After running for a while, t will actually grow large, as you can see here. It will grow large, and the floating point precision of the STD sine degrades. And because large inputs push operating range where float cannot represent the fractional part of the number accurately. So after a few hours of continuous playback, the pitch would actually drift. So instead, what have I done? We are going to use a phase accumulator. We maintain a variable called phase that starts at actually 0 and increments by a fixed amount called phase increment on every sample. The phase increment is 2 times pi times the frequency all over the sample rate. Now when phase reaches 2 times pi, we wrap it back to 0 because phase always stays in the range 0 to 2 times pi. So the input to the STD sine stays actually small, and the precision remains constant, like continuously or forever. So this is a standard technique for digital oscillators, and it is what you should use every time you need to generate a periodic signal. Okay, so we want to now start coding. We want to include the CMath. So this CMath is specifically for waveform generation. The sine, we want to define our own pi constant. So we're going to do a static. What we're doing here is actually defining our, you can just comment the pi constant. We need to tell it to play the sine wave at for about 5 seconds, then stop. So we need to, now we want to do an audio callback function. So the function is actually going to run on the audio thread. So in this function, as you can remember, I told you everything running inside this function must be real-time safe. So we're not going to do no malloc, no free, no mutex, no input output, no system calls. So we're going to do a static int audio callback. Okay. So I'll just explain here a bit what I am doing here, because it's very much important than so that is it. So let me walk you through from the top what we have done, because there are important decisions embedded in what looks like hello world for audio. So at the top of the file there's the includes, so we pull in the CMath for, of course, for waveform generation. We pull in the stdio for the outputting, that is the printf. There's the stdlib, of course, for exit and error handling, and there's the PortAudio header. So this is we are actually we are actually calling the PortAudio library. So there are no standard library containers, no strings, no input output stream. This is not an accident. We are writing code that will eventually run the audio on the audio thread. So so every include you add is a temptation to use something that is not real-time safe. So that's why I was a bit hesitant at the beginning and careful on what I am actually including. So there are some constants here. I have named them the K frequency, for example, at 440, the K sample rate. There's the K buffer size. There are no bare numbers in this file. If you see the number 256 someplace in a function, you know exactly what it means because it is actually named. So this discipline actually matters more in larger files, but we practice it from the start. So there's a sine generator struct. So this struct is our way of passing state to the callback. PortAudio actually uses a C-style function pointer for the callback, which means we cannot use a C++ lambda with captures. If you don't understand what a lambda is, please go back to and understand the basics of C++. So we cannot use a member function. We actually have to use a free function that takes a void pointer, and we have to cast that void pointer to our state type inside the callback. So this is a pattern you will see in every C-based audio API, and maybe Core Audio's render callback works the same way. So as we continue, so now the callback itself, this function, the callback function, this is actually a function that runs on the audio thread. I want you to look at the signature. It's actually returning integer and text 6 parameters. So the input buffer is null pointer. Why am I using a null pointer? Because we have specified there is no input stream. The output buffer is the memory we must fill. Frames per buffer is actually telling us how many sample frames we need to produce. And of course there's the user data. The user data is actually our state pointer. So inside the callback function, we are doing something we call I'm actually casting user data to our sine generator pointer. Then we cast output buffer to float point because we told PortAudio we want 32-bit floating point format. Then we loop through the frames per buffer iteration. So each iteration computes one sample of the sine wave and writes it to both the left and right channels of the interleaved output buffer. So if you don't understand, please, you can go back, you can pause the video and go back and understand. So the interleaved format deserves attention. In an interleaved stereo buffer, the samples are normally arranged as left, which is 0, right 0, left 1, right 1, left 2, right 2, and so on as you go forward. So for frame I, the left channel is at index 2, is at index 1 times 2, and the right channel is at index 1 times 2 plus 1. So we actually write the sample, the same sample to both channels because we are generating a mono sine wave. If you wanted a stereo effect, for example, say for example panning, the tone to the left, we would scale to the left. We will actually scale the left and right channels differently. I will show you as we progress. We are doing something, I am doing something like a phase accumulator here. I'm doing something we call a phase accumulator logic. So this is the core of the oscillator. So we start with phase at 0. Each sample we add phase increment, which is here. We are adding phase increment, which equals to 2 2 times pi times 440 all over 48,000. So after approximately 109 samples, the phase reaches 2 times pi, and then we subtract 2 times pi to wrap it back. So this wrap is very, very critical. Without it, after 1 hour of playback at 48 kilohertz, phase would reach approximately 2 times pi times 440 by that 600, so which is roughly 9.95 million. So a double has about 15 decimal digits of precision. So at a value of, say, for example, that 9.95 million, the fractional part, the part that determines your position within one cycle of the sine wave, has only about 8 digits of precision left. So this will mean your 440 hertz pitch is now only accurate to about 0.0001 hertz, and the harmonics of the waveform are visibly, so after several hours the output will be audibly wrong. So wrapping the phase actually prevents this entirely. So there's the main function. So in the main function, this is pretty basic. I am actually initializing PortAudio. I'm initializing PortAudio. We are preparing our state. We are configuring our output parameters and opening the stream. The PA_open stream call is where we specify everything. We are actually specifying everything, including, that is, the sample rate, buffer size, formats, the callback function, and our state pointer. So after the PA start stream, the audio thread is running right now and calling our callback at regular intervals. So we sleep on the main thread for 5 seconds, then stop and clean up. Why 5 seconds? You remember we defined 5 seconds over here. Yeah, so one thing to flag here is about the main function. I want you to notice that I am pre-calculating the phase increment before starting the stream. I want you to check it clearly. So you see, I'm incrementing it before starting the stream. I do not want to compute it inside the callback. So I want us to run this now. So if you have been following, when you run these, we are going to hear a clean steady tone at 440 hertz. So we need to build the executable. Cmec build, of course, target. What did we call it? What was the target? Yeah, here we go. So this was the target name. Copy and paste it here. Then we're going to do so it's building, so it's built. Then let's just run it. Build. Okay, no. Build. Then the sine of generator PortAudio. Perfect. and it works. So final phase 1.304 radian. And that's, ladies and gentlemen, we've made our first sine wave generator. So see you in the next video, as we are going to talk about measuring actual callback timing. Thank you for watching this episode. Bye.